Stanford University.
Hello. Welcome to W380 2010-2011 Spring Quarter. I'm Andy Freeman. The other organizer of this class is Dennis Allison. The quarter's winding down, so be sure to keep up with your assignments. Remember, no incompletes. So far this quarter, we've been hearing a lot about intellectual property and other high-level concepts. Today, we go the other direction, down to device technology. We live in a world dominated by CMOS because it's good enough on all the crucial characteristics. As some of us know, there have been lots of competitors that have failed because while they were great on some characteristics, they just weren't good enough on enough of them. And so their promise was irrelevant. Carbon nanotubes are yet another promising technology for building energy-efficient systems. However, as before, their energy efficiency is going to be irrelevant if we can't figure out how to build large enough systems out of them, if we don't have the equivalent of self-aligning gates and a few things more. Today's talk by Professor Mitra is about the challenges of building systems out of carbon nanotubes and some of the ways they might be overcome.
Thank you very much. I'm very honored to be here giving this 380 seminar. I used to be a student at Stanford. And I graduated, went to Intel. I guess that's where I got purified, and and then I got back over here, and I'm here, getting all this glory, giving this talk, but all the work has been done by an amazing set of students, whose names are over here, and Professor Philip Wong, who is in the Allen Building or the CIS. He is my collaborator on the device aspects of these carbon nanotubes, and it has been a great ride. And the thing that is most exciting about this project is that I learned a lot about device technology, about fabrication and design by going through this process. By the way, please feel free to stop me and ask questions. Is that the way we do this seminar? Yeah, sure. Okay. And this is a reconfigurable presentation, which means that I can skip slides, right, if need be. Okay. So carbon nanotubes are rolled up cylinders of graphene with some amazing electrical properties. Carbon nanotubes, Ijima Sensei from Japan, he has a lot to do with these carbon nanotubes. He found them. And these cylinders of graphene, as shown in this cartoon, you would see a typical diameter between 0.5 through 3 nanometers. The carbon nanotubes that we grow in the CIS building right across the street, our diameters are somewhere around 1.2 to 1.5 nanometers. So what can you do with these carbon nanotubes? A lot of people talk about making wires out of carbon nanotubes, and there has been some very significant work that has happened in that space. What I will be focusing on is using carbon nanotubes as channel materials in transistors. So here is a cartoon where you can see these carbon nanotubes. So you have grown these carbon nanotubes on a substrate, and I will be going a little bit into like how you grow and do all those things. Or you transfer carbon nanotubes from one substrate to another substrate, and then what you do over here is that you build a gate. So for example, this could be something like an hafnium oxide, and then this could be a metal gate. Look at the part of the carbon nanotube under the gate. That part is supposedly undoped, right? Because that's like an intrinsic material. And if these carbon nanotubes are semiconducting carbon nanotubes, that means that they will have some sort of a band gap, which means that depending on the voltage on this gate, you will be able to control whether there will be current flowing through this carbon nanotube or not. That would make a transistor. And are these transistors real? Yes, here is an SEM image. You can see these carbon nanotubes and you can see the gate, right? So we made a transistor. The next question is, well, if we can make a transistor, we should be able to make some sort of digital logic out of these carbon nanotubes because we got a switch. And here is what I'm going to show is a carbon nanotube field effect transistor inverter. So essentially, you got carbon nanotubes shown in this cartoon, and the top part is the p-FET part, and the bottom part is the n-FET part, just like in a complementary transistor. There are a couple points to note. The carbon nanotubes are grown on a substrate by chemical synthesis or transferred. So that's why fundamentally there should not be a limit to how much density you can get, or so to say that you should be able to get very dense arrays of carbon nanotubes. So if you could achieve very dense arrays of carbon nanotubes, which is a very difficult goal right now, you should be able to get somewhere around a spacing of 4 nanometers, which would mean roughly around 250 carbon nanotubes per micron. And I will come back to this density issue later on, but this is a very important issue. So, but along the y-axis, you are making these contacts, these gates using just classical lithography, which would mean that you are limited by the lithographic pitch along the y-axis. Along the x-axis, you are limited by whatever the density of the carbon nanotubes you can grow. Make sense? So let's look at some of the milestones about the carbon nanotube technology. So carbon nanotube technology is a very exciting and a very promising technology. Why? Actually, there was a very nice paper that was written at the device conference IEDM in 2009 from IBM in collaboration with Philip Wong at Stanford. And what that paper says is that if you consider, for example, an 11 nanometer technology, and if you compared some sort of SOI technology at 11 nanometer with silicon CMOS, and if you considered perfect carbon nanotube technology, right? And perfect is a very important word over there, where you could overcome a lot of the challenges that I will be talking about, and you could have a very high density of carbon nanotubes. Then you could potentially achieve very significant benefits. That is, at the same power level, you could run at 5x faster speed. And they some sort of model, some sort of a multi-core processor and all that, which would mean that if you consider from an energy standpoint, you're talking about at least an order of magnitude improvement in energy using a carbon nanotube technology. So that's a big deal. But again, that was a modeling sort of a paper, modeling and optimization sort of a paper that talks about what do we have to gain if we could make a technology like this. And as I said, we are very far from achieving those goals, but we have made a lot of progress over the last 5 years that I'm here to talk about. So let's look at this carbon nanotube technology. Around 1998, that's when Delft University and IBM, they showed the first carbon nanotube FET. So it's been almost 12 to 13 years since the first demonstration of a carbon nanotube FET. 2001, IBM showed a single carbon nanotube logic gate. Now, this single carbon nanotube is a very important aspect over here. What they did is that they said, okay, so when I was showing you the CN FETs, I showed you many carbon nanotubes under the transistor. But over here, they were doing with a single carbon nanotube in that gate region. Now, these are very significant scientific achievements, because without the foundations that have been laid by these people, some of the work that we have been able to achieve would be nowhere. Okay. So in 2004, actually that's the record on the best single carbon nanotube CN FET. This was done at Stanford by Professor Hongji Dai in the chemistry department. And in 2006, this is a very famous paper, many of you are familiar with this one, where IBM showed a ring oscillator out of a carbon nanotube. What they did was that they had a substrate that they had a lot of carbon nanotubes. They found a particular carbon nanotube that was useful for them because this was a semiconducting nanotube, and they built a ring oscillator on that semiconducting nanotube. These are very important scientific achievements. So the carbon nanotubes have big promise, but there have been major barriers that stopped the community from being able to achieve VLSI out of carbon nanotubes. You will all agree with me that the examples that I showed before are not VLSI. So So what are the major barriers? Actually, there have been two very significant barriers. The first barrier is the barrier due to mispositioned nanotubes. So since I was doing PowerPoint where on that slide that I had the inverter, all my carbon nanotubes look very nice, right? Modulo my artistic capabilities. Versus when you grow carbon nanotubes, you would see something like this, right? Now, if you have carbon nanotubes, something like this, some carbon nanotube passing like this and so on, essentially what you will see is you will have incorrect logic. And I will show you some examples later in this presentation. So that's one big challenge. The second challenge is the challenge of metallic carbon nanotubes. So when you grow carbon nanotubes, not all carbon nanotubes are semiconducting carbon nanotubes. There will be carbon nanotubes that would be very leaky. Their band gap is almost close to zero, which means that they will always conduct. What does that mean for digital designers? Well, if you had an inverter and you have these transistors over here, you have shorts between the source and drains of your inverters, of your transistors. Now, you would not like that, right? So these are the two fundamental reasons why people couldn't build very large-scale carbon nanotube circuits. And the materials folks, they have done a phenomenal job in trying to see how much progress they can make. And it's almost in a situation today where people have made good progress, but it's almost impossible to absolutely solve both of these problems completely in the materials world. So processing alone is inadequate to be able to solve all these problems at a large scale, right? We are talking about billions of devices in the future if this technology has to take off. So the point that I'm going to make is that you have to mix processing with the right amount of design, and that's what we call imperfection-immune design. And by doing that, we will be able to demonstrate that we can overcome these challenges and build something that looks more close to larger scale integration than the single CNT demonstrations. So what do mispositioned carbon nanotubes do? So here is a cartoon. So for example, you are trying to implement some complex logic function out of this carbon nanotube circuit, and if there was a carbon nanotube that was just curling like this, and we have many such carbon nanotubes, I can show you images, what would happen is you wanted some functions over here and you got entirely different functions over here. So you have clearly a problem with logic functions. If you had metallic carbon nanotubes, so as I was saying before, this has to do with what is called the chirality of the carbon nanotubes. What that does is that it's essentially the direction, the orientation in which your sheet of graphene rolls to form a carbon nanotube. So for a semiconducting carbon nanotube, you would want the current to be controlled by the voltage, but for a metallic carbon nanotube, there is no gate control. Now, typically when you grow carbon nanotubes, you would get roughly around 10 to 50% of the carbon nanotubes that you grow to be metallic. And the question is, hey, how can you build logic with these situations?
Well, at least it's an ideal current source.
Sure. No. So the results that I'm going to show you today. So yesterday, people were building, like almost probably it's of the scale of SSI, maybe, like small scale integration or something, the single CNT ring oscillators. I'm going to show you some imperfection-immune VLSI circuits that we could build, and we could do this at a full wafer scale. So it's not that we can just do it in one place on a wafer. I'm going to show you, for example, things like arithmetic circuits. I'm going to show you latches and so on built out of these carbon nanotubes. So what were the milestones since 2006? So our group at Stanford, we could show at a full wafer scale these logic gates built out of carbon nanotubes at a full VLSI scale, at a full wafer scale. These were at a 4-inch wafer scales. This is a paper that got the best student paper award actually at the VLSI Technology Symposium, and I was told by several colleagues that this was probably the first time that a carbon nanotube paper got into that conference, because people are very practical over there and they want to see real results that could be used in real life. Another event that happened from our group in 2009 were these imperfection-immune adders and latches that we could show out of these carbon nanotubes. we could actually show three-dimensional circuits that were monolithically integrated without having to use any sort of through silicon vias and all that. So for those of you that do IC design, you know that we have our transistors at the lowest layer, and then we have stacks of wires, right? Instead of that, just think of a situation where you could place transistors in any arbitrary layer that you want, with wires in any arbitrary layer that you want, and that's what we actually achieved in this IEDM paper in 2009. We could show up to 3 layers, and there is no fundamental reason why you couldn't do beyond 3 layers. And the good news is that several other groups are also interested in this carbon nanotube, so we are not the only ones, right? The Illinois folks showed carbon nanotubes on flexible substrates, which is also very exciting. The USC folks, they showed defect-tolerant logic gates, and one of the coolest things I was telling Dennis about it is that in this field, I think it is very important that whatever we do or whatever we claim, other people should be able to reproduce our results. Otherwise, this field is not going to go anywhere. And we saw that. So a lot of our techniques, we published, and then people were working with us, and they could reproduce the same results in their labs, which had been very satisfying. And IBM actually has been pushing this carbon nanotube fits to ultra small geometries. They have a very recent Nature Nanotechnology paper that talks about very fine geometries, I think 50 nanometer or something like that, showing carbon nanotube fits and their properties in those domains. So if you look at the technology outlook of what has happened, so positioning and alignment, it was really a red light when we started back in 2006. With some of the techniques I'm going to show you, it has become a green light, and I think that is agreed by the whole community. So far as the metallic carbon nanotubes are concerned, with the techniques that I'm going to show you, we were able to overcome the challenge, but still it would be great if the chemists could grow carbon nanotubes with a smaller percentage of metallic carbon nanotubes. They don't have to achieve 0. If they can achieve 1% metallic carbon nanotubes rather than 33%, that will go a long way, and some of our techniques will even get better. And that's why we have a yellow and a green light at once, basically, for this one. Carbon nanotube density is still a big challenge, but I'm very proud that one of my undergraduate students very recently has been able to come up with a very cool technique, which it seems that should be a scalable way of increasing density of carbon nanotubes. He had a paper just published in Nano Letters, and he's kind of working on that to make that further scalable in the future. So we have a lot of hope for that, and several of our colleagues and collaborators are working on aspects of doping and the contacts, which is also something very important for this carbon nanotube FET technology to be a reality. Any questions until now, or let me move into how do we achieve all this? So as I said, that mispositioned carbon nanotubes create incorrect logic functions. So we have to have a way of building logic gates that are inherently immune to these mispositioned carbon nanotubes. So I would like to just grab your attention for the next few minutes, because I'm going to do a small animation to show you how you can do this for a simple NAND gate. And then you can trust me that I can do this for any arbitrary function. So let's look at the NAND gate. So what do we do? Well, first you grow nanotubes, and the nanotubes came up like this. I do not know. I do not have any idea of how the nanotubes will turn out to be. This is something very important, because I'm not going to look at a wafer and change my layout or something based on that wafer. I'm going to do full VLSI. I'm going to create a layout that will guarantee that doesn't really matter how mispositioned these carbon nanotubes are, you will have the correct NAND gate. Okay? So I have the carbon nanotubes like this. I don't know how they were grown. So for a NAND gate, as you know, that for the pull down you have 2 series transistors, and for a pull up you have 2 parallel transistors, right? But instead of drawing 2 parallel transistors on the pull up, what I did is that I just created a huge extended gate over there. And this is something very crucial. This is actually one of the most crucial steps why I can do what I claim I can do. So once I have done this extended gate, next what I'm going to do is that I'm going to etch this particular gate, this extended gate, and the carbon nanotubes underneath it. And that's it. This etch region is going to guarantee that this particular NAND gate is going to act as NAND gate as long as the carbon nanotubes go from here to there and they just do not spiral, all my nanotubes do not spiral over here. And the simple-minded explanation of why that's the case is because when you have carbon nanotubes that go from, let's say, the VDD to the output, either a carbon nanotube goes under gate A or a carbon nanotube goes under gate B. Now there could be a carbon nanotube that goes under gate A and B, which is fine because that would kind of create some sort of a function of, like an AND of A and B basically, while you are wanting an OR, and AND is a subset of OR, so that's fine. But any other carbon nanotube that could potentially create incorrect logic, for example, you could have a short over here, for example, would have at least one of its parts being removed by the etching process. That's the guarantee. And I'm going to go through a formal proof to show how you can do this for arbitrary functions. So the key point is that there are graph algorithms that you can come up with that you can create these imperfection-immune logic functions for any arbitrary logic functions. That's the important point. So what are the algorithms we are talking about? Well, you could give me a layout and you could ask me a question that is this layout immune to mispositioned carbon nanotubes, right? And let's look into that. So again, I take my NAND gate that I was showing over there, and remember this was the gate A and this was the gate B and this was the etched region that I was talking about. Now once you have this kind of a layout of a library cell, actually you can build a graph out of that. And this is the graph, and I'm not going to drag you through the details of how this graph is constructed. You can trust me, this graph is correct. What this graph really does is that any carbon nanotube situation, any carbon nanotube that can go from this contact to this contact can be represented as a path from this contact node to this contact node in this graph. So any carbon nanotube situation, for example, a carbon nanotube that goes through contact, gate A, through this diffusion region, gate A, diffusion region to the contact, will be shown over here, contact doped, gate A doped contact. That would be a carbon nanotube, for example. Okay. Now what I also did is that for each of these nodes I have assigned a logic function. For example, the contact logic function is 1, which means that if a carbon nanotube is connected to a contact, it will always conduct over there. In a doped region is the same, versus in the gate A region, when the gate A is activated, that's when the carbon nanotube will be passing current, otherwise it would not be passing current, and so on. Okay? And now let's look at some examples. For example, if you had a carbon nanotube as shown on the right, a situation like this, that would be represented by this path, orange path, contact doped, gate A doped contact, and that's written over there, and that path has a logic function implemented which is function A, right? So this carbon nanotube will be passing a current when the gate A is activated. Similarly, you have another path over here which will be path B, which is shown over here. You could have a weird path as shown over here, and this particular path is shown as this particular path over here, contact doped, gate A doped, gate B doped, doped contact, for example. And this path has a logic function A and B. So you keep doing this, you enumerate the paths, and then at the end, and by the way, if you have a carbon nanotube which goes like this, goes through the etched region, that has a logic function of 0 because that carbon nanotube has been cut off basically. So if you keep doing this and enumerate the paths, finally what you will find is that the logic functions that these paths implement that are A or B or A and B or 0 and so on, which is the same as A or B, which you wanted to implement in the pull-up of a NAND gate. So this is a correct implementation no matter how mispositioned the carbon nanotubes are. Now the second question that you could ask is that now that you gave me a logic function and you want me to give you a mispositioned carbon nanotube immune layout for an arbitrary logic function, and I could do that too. What would I do? Well, for example, you have this function where you got A and then B and C or D or E in parallel and so on, and essentially given that logic function, I will tell you, well, as long as you have your H regions defined over here, that will guarantee that this particular logic implementation will be immune to mispositioned carbon nanotubes. So number one, couple points to note. This technique that we are talking about unlike classic defect and fault tolerance techniques that a lot of people have talked about in this domain, now we are immune to a large number of mispositioned carbon nanotubes. We are not talking about, well, can we do single correction, double correction, and so on. We are saying as long as the carbon nanotubes go from north to south, I am okay, I can be immune to a large number of carbon nanotubes. And number two, this implementation is very efficient because at the library gate level, your areas might increase a tiny little bit, but you have not added any sort of a major redundancy or something like that. And if you look at modern chips, most of the area is dominated by wires. So even this increase in the sizes of the library cells would not have a very significant impact in how your overall chip is going to look like. So we have hidden all the problems at the library cell level and been able to solve this problem. But most importantly, this is something that's forgotten many, many times. This kind of a technique is compatible to VLSI processing because I didn't need to know anything about my wafer to be able to print these gates. So I do not need any die-specific customization, which is something very important. The whole reason that we can do all this Moore's law and all that is because we keep printing the same thing over and over again in a very parallel way. And that's what you can do with this technique. And also, since we have hidden all the details about this layout at the library cell level, no one else, a designer doesn't need to know anything about whether I'm using carbon nanotubes or anything. That will happen at the last technology mapping step of my VLSI design flow. So literally, any of you can write a Verilog or a system Verilog code and push a button on Synopsys design compiler, and you can create a carbon nanotube circuit. So I have not changed the overall stack of the VLSI design flow that makes it highly attractive. Okay, so I have shown a lot of theoretical stuff. Let's look at some pictures to make sure that these are really real. So if you grow carbon nanotubes on silicon substrates, you get what I call a bowl of noodles, right? And versus if you grow carbon nanotubes on a quartz substrate, and by the way, our group has been able to demonstrate the first wafer scale aligned carbon nanotube growth, and you will see all these equipments in the CIS building right next door, and we'll be happy to give you a tour if you're interested. You see this is how the carbon nanotubes look like. And this is at a full wafer scale, you can see the carbon nanotubes. Good point, you got 99.5% alignment of the carbon nanotubes, which is very good, which is like, that's why things go from north to south. But any of you will agree with me that a 0.5% of a billion is a very large number, and that's why you need processing to do a good enough job, as I was saying before, plus you need the imperfection-immune design technique to make up for the rest. And since the imperfection-immune design technique is so inexpensive, it makes sense to build logic gates and logic structures out of these things. So we have grown carbon nanotubes on quartz, right, on this slide. But for silicon processing, you would want carbon nanotubes on silicon. And what do the students do? Well, they use a thermal release tape, almost like a sticker, to transfer carbon nanotubes from quartz to silicon, and from a quartz substrate to a silicon substrate at a full wafer scale. And this might sound funny, right? This looks almost like a hack, but this particular transfer step we have found this to be a key in being able to achieve a lot of things. Look at this transfer can be done at a very low temperature, 90 degrees to 120 degrees C. Now think about that, if you can transfer from one substrate to another substrate, nobody has said that you can do it one time. You can keep transferring multiple times from multiple source substrates to the same destination substrate, and your carbon nanotube density should go up. That could be a way to increase carbon nanotube density. Now life is not that simple because you have to worry about a few things, and that's exactly one of the undergrad students in our lab was able to achieve in his nanolaters paper. By doing this transfer in a very clever way, he could linearly increase the density of the carbon nanotubes on the destination substrate. Nobody has said that you have to transfer this carbon nanotubes only on the same layer. So you transfer this carbon nanotubes on layer 1, create your imperfection-immune circuits, build a dielectric, and then since it's a very low temperature process, you transfer your carbon nanotubes on layer 2, build your circuits, layer 3, build your circuits and keep going. That gives you the monolithic 3D circuits out of this carbon nanotubes. I'll show you some pictures of that later. So this transfer step, we found it to be very useful. And this was back in 2008, where we were able to demonstrate actual logic gates, complex logic gates and/or invert, or and invert, you just name it, using this carbon nanotube, mispositioned carbon nanotube immune design technique. So for example, here is the pull-up of the NAND gate. You can see this is the H region that I was talking about before, and that actually gets printed, and you can see the correct behavior of a NAND pull-up if you have current on the y-axis and actual states on the x-axis. So this was the first paper where at a full wafer scale you could show correct logic gates with carbon nanotubes. Now to be able to build circuits, you cannot stop at logic gates. You have to be able to connect logic gates up in a cascade, and you have to build storage elements, and you have to build complex circuits. And the reason that was a showstopper is because of the metallic carbon nanotubes. So now that we solved the problem of mispositioned carbon nanotubes, our next challenge clearly was, how do you deal with the metallic carbon nanotubes at a VLSI scale so that you can create cascaded gates and arithmetic circuits and storage elements and so on. And that's what I will focus on in the next part of the presentation. But before that, if you have any questions, I'll be happy to take those. Yes?
On the picture showed for a gate several nanotubes in parallel.
Yes.
Why?
Because what happens is that when you have a quartz substrate, and this is very well known in the material science literature, that when you grow carbon nanotubes, the carbon nanotubes actually follow the crystal structure of quartz, and that's why you get this highly aligned carbon nanotubes along the crystal structure, versus when you have a silicon substrate, the carbon nanotubes just grow everywhere like a bowl of noodles.
No, it's not. Why are you making the metal big enough to cover several nanotubes instead of...
Okay. Why do you have several nanotubes under the gate? That's what you're asking.
How much current can you get through a
nanotube? So for example, you can get currents of the order of like hundreds of microamps basically out of these nanotubes. But the thing is that if you have to this is related to sizing, right? Because if you have to drive something bigger like a fan out of 4 or something like that, you will be needing more nanotubes. Now this becomes more important in the last part of this presentation. I will be talking about variations. So what would happen is that even if you grew carbon nanotubes, you thought that the carbon nanotubes would grow in a very uniform way. But in reality, what would happen is that you would have spacing variations among the carbon nanotubes, and because of the spacing variations, you may not be able to guarantee that how many carbon how many carbon nanotubes will be passing under your gate, and you may want to do some sort of bigger sizing to guarantee that certain number of carbon nanotubes pass under your gate. So even there we will be playing some clever layout design tricks. But that's a reason why you want multiple carbon nanotubes under a transistor. Another reason to get multiple carbon nanotubes under the transistor is, if you look at, for example, the diameters of the carbon nanotubes, there would be variations. So if somebody wants to work on variations, this carbon nanotube is a perfect technology for that, because you have a lot of variations. But at the same time, if you have bigger gates with more nanotubes under the gate, essentially what will happen is that some of those variations effects will average out. So these are like multiple various reasons why you would want multiple carbon nanotubes under a gate. Yes?
You said it covers most errors. That sort of implies there's still some that it's not capturing.
Right. So for example, so I showed that H region, right? Remember, for the NAND gate? Now think of a situation where all my carbon nanotubes that I ever grew were just curling up in that particular H region because I was so unlucky. Then I couldn't do anything about it, right? So that's why it is very important. So I'm not claiming that just by doing design you solve all the world's problems. That's why what is most important is a processing and design co-optimization. So processing has to go through a long step so that it's at the right situation where now design can come in and solve the problem. But any one of those on their own cannot really achieve our final goal. And that's what we found over and over and over again working on this technology. Make sense? Okay, so let's talk about metallic carbon nanotubes. So to remind you, well, we want transistors with metallic carbon nanotubes. What you got is just, ideal current, right? So what are we going to do about it? Well, here are a bunch of options. Well, of course, one option is grow 0% metallic carbon nanotubes. And somebody told me that, if somebody can achieve the 0% metallic carbon nanotubes, that person is going to win a big, big prize, basically. And okay, so if we cannot grow 0% metallic carbon nanotubes, what can we do? Well, people observe that, okay, maybe we can remove metallic carbon nanotubes after growth, right? That would be pretty nice. The trouble is that, you are talking about digital systems, right? You are talking about digital systems that should have low leakage, right? And if you have to have low leakage, you have to have a large number of these metallic carbon nanotubes to be removed. And if you do the numbers, which some of my students sitting here did, you would find that you would need 99.99% of the metallic carbon nanotubes that have to be removed, right? And I will show you later that just removing metallic carbon nanotubes alone is not even going to be enough. But the removal is the first step, but even that removal has to be at a very high rate of removal. So let's look at some of our options of removal. So the first option, and there is some very interesting work that has happened in this space, is sorting of carbon nanotubes. So they would place carbon nanotubes on some sort of a wafer, and then they will do some sort of a processing so that the metallic carbon nanotubes will run away and the semiconducting carbon nanotubes will stay around. That's kind of the high level idea. It's a very promising idea. The only trouble is that not 99.99%, which is very important for my digital VLSI. There is another idea that was published from IBM in 2001, where the idea is that, well, why don't you pass a lot of current through a carbon nanotube and the metallic carbon nanotubes will break? And we call that technique SDB, or single device electrical breakdown of carbon nanotubes. Now that technique alone is not going to be very scalable, but to prove that, let me show you some actual example. So let's say here is the SDB technique. So let's say that you have a carbon nanotube field effect transistor, and the blue ones are your metallic carbon nanotubes and the orange ones are your semiconducting carbon nanotubes. And what you will do is that you will turn the gate off by applying appropriate voltage, and then you will be applying a very high voltage so that there is a lot of current, and these metallic carbon nanotubes will pass a lot of current, and because of self-heating they will break somewhere. So what would happen is, for example, over here, as you can see, that the metallic carbon nanotube got broken over here, right? It's a very useful lab tool, and we have been able to replicate this technique in our lab, and we could show that if you look at the ion I off, basically, you can very significantly improve ion I off by using a technique like this. The only trouble is, if you are talking about a large scale design with billions of transistors, you cannot go and contact each of those transistors separately to be able to do this SDB. And in a large VLSI chip, you do not even have access to the intermediate nodes of that VLSI chip, which means that you will end up with a situation where there will be these fragments of metallic carbon nanotubes that will stay. And those fragments of metallic carbon nanotubes will actually create incorrect logic. So let me show you an example of that. Forget about the pull-up network. Here we are going to focus on the pull-down network. And let's say this was a metallic carbon nanotube, this blue carbon nanotube shown over here. And I applied a very high voltage at these two accessible nodes, the ground contact and the output contact. And a lot of current was flowing. I configured the gates so that they are turned off. What happened is that this metallic carbon nanotube did break, but it broke over here. And the logic function that I got is C or D because the metallic carbon nanotube did not break over here. So that's a problem. So what do we do about it? Well, so we have a technique which we call VMR, and VMR stands for VLSI metallic carbon nanotube removal. What we are going to do is we are going to again use a design technique and do some processing on that design technique, and by doing that I will show you that all those problems will be gone. And this technique is sufficient for all logic designs. That means you just give me a logic design, I'll be able to create that logic design and implement that using this VMR technique. And again, just like the previous mispositioned carbon nanotube technique, this you would not need any die specific customization. And again, everything will be hidden at the library cell level, so you can press the Synopsys design compiler or Cadence, or I'm not advertising for Synopsys over here, and you will be getting your carbon nanotube circuit. So how does it work? So I will show you for a simple example. Let's say you have two inverters and the NAND gate, and let's say this was the final layout that you wanted to create. So what would we do? So this is where we will start. So of course we grow and transfer carbon nanotubes from the quartz substrate to the silicon substrate, and this is how it looks like. The blue ones are the metallic carbon nanotubes, and the orange ones are the semiconducting carbon nanotubes. This is how the substrate is. And if you look it from the side, it will look like there is a backgate oxide, and there is a large silicon backgate over here. Now what I will do is I will create these interdigitated electrodes all over, and this is what we call a VMR structure, right? So with metal we created interdigitated electrodes, and this structure is highly friendly to metallic carbon nanotube breakdown, because almost everything is accessible from this almost what I call a dumb layout structure, right? So what do we do next? Well, now we actually perform electrical breakdown. As shown over here, I apply a high voltage. Now to be able to do the electrical breakdown, I have to be able to turn off the carbon nanotube FETs. Now if you have to apply a very high voltage, and if you have to rely on a top gated carbon nanotube FET, then the oxide of the top gated carbon nanotube FET has to be very thick, and if you have very thick oxide, your performance will be limited, so you cannot do that. Instead you start with a very thick back gate, and you turn off the carbon nanotube FETs basically using the back gate, and then you perform this electrical breakdown as shown over here. Now once you have done this breakdown, then what you do is you etch out the carbon nanotubes, just like the previous etching that we were doing from predefined regions when we did the layout design, and that's using this misposition carbon nanotube immune design technique that we showed before, right? So we did that. One of the key points why we were able to achieve this, we tried many other techniques, and finally we nailed down to this particular technique. One of the very important points of this technique is that, look, the places where you will finally have your carbon nanotube FETs, the contacts are not removed from those places. The contacts stay intact. Instead, we were trying previously some sort of a deprocessing technique, and there the contacts were all getting messed up, and this was a very important point that we had to kind of get through to make this technique work. And then you just go your top gates, you just create your oxide, create your top gates, and you do some more etching using the misposition carbon nanotube immune design, and you connect wires and all that, and you got the final intended design that you wanted. Now you must be wondering that I just showed that toy circuit, is this really going to work for any arbitrary design? And here is a theorem which I am not going to prove, but it's fairly straightforward. The point is, even if you start with that strange dumb structure, the interdigitated electrodes, that was the VMR structure, you can prove that you can create any arbitrary layout, any arbitrary logic design by etching out parts of that VMR structure, as long as you just satisfy one condition. And the condition is very simple. The condition is that if you have in any library cell two transistors in series, then they have to be connected through a contact at minimum pitch. Essentially what's going on, if I go back to my previous slide, these VMR structure fingers are essentially becoming those contacts, and that's why you need those. And the reason you need them at a minimum pitch is because you want to make sure that every segment, every fragment of a metallic carbon nanotube is broken down, so that you do not have this metallic carbon nanotube fragment staying and messing up your logic. Basically that's essentially what's going on. And again, this is a small change in the library cell level, and with all these new layout rules that people are using for restricted layout design rules and so on in smaller technologies, these are very compatible with some of those layout rules that allows you to do these immune library cells at a very small impact. Okay, so we used now this misposition carbon nanotube immune design and this VMR technique, and we were able to demonstrate, for example, arithmetic circuits and storage elements at a VLSI compatible way. So for example, here I'm showing you a half-adder sum circuit basically, and here I'm showing you a D-latch, and these were actually the first experimental demonstrations that you can do all these things in a VLSI compatible way with these carbon nanotube circuits. And this is the 3D circuit that I was talking about. As I said before, when we go and create integrated circuits, we typically have all our transistors at the lowest layer, and we have only layers of wires. Now think of a world where you will have transistors and wires on all layers. Now people are already talking about some of that stuff in the context of, for example, 3D using through silicon vias, where they will be taking 2 silicon chips and they will be kind of stacking them up. But here the cool factor is that you do not need any of those through silicon vias or anything. You just do your layout design having your transistors and wires on any layer that you want. You still have to figure out when those transistors and wires work, how you dissipate how you get the heat out, and we can have a long discussion on that. But this is a highly scalable technique for this. The reason, a lot of people tried this. And one of the fundamental problems why it's not easy to do something like this with conventional technologies is because when you create transistors at upper layers, you need a very high temperature typically. And if you do transistors at that very high temperature, the things underneath will melt away. Versus over here, because the transfer technique that we were talking about, that was a low temperature process that actually allowed you to do this thing, where essentially, as I said, you transferred carbon nanotubes, so you're decoupling the high temperature growth from the low temperature transfer, and then you remove the metallic carbon nanotubes, fabricate, create vias and interconnects, create a dielectric, and you move on, and you will create your multiple 3D monolithically integrated 3D carbon nanotube circuits. Is this something real? Yes. Here is one example. Just for fun, we created a 2-layer XOR gate basically, just to show you that you can do almost anything. We had up to 3 layers demonstrated in our IDM paper in 2009. So now that we have dealt with the technology problems, by the way, are there any questions at this point? Yes. No, we have problems with CMP basically, because like when you have things on the second layer, you have to have a very good planar structure so that you can go and do a very good sticking with your new set of carbon nanotubes that you will be transferring. Yeah, it has to be a very polished surface for that. Yes. Any other questions? Okay. So now that we have talked about solving the technology problems using this imperfection-immune design approach, now have we solved all the world's problems? Clearly not, because you have to worry about carbon nanotube variations. What really happens? Well, if you look at carbon nanotubes, there are many sources of variations. For example, you could have variations in the diameters, as this gentleman was asking me before. Now, as I said, that if you have a lot of carbon nanotubes under a gate, then these diameter variations become somewhat smaller. Versus if you look at the density variations of these carbon nanotubes, they become very prominent, and I'll be talking about that. And even the metallic carbon nanotubes, I removed the metallic carbon nanotubes after growth, right? And what essentially that translates into is variations in the density of the carbon nanotubes, because now I have some useless carbon nanotubes that are sitting over there and not contributing to my currents. So as a result, probabilistic modeling is going to be extremely important if you build circuits and systems out of these carbon nanotubes. Let me show you some cartoons. So let's take a probabilistic carbon nanotube growth model, right? So when you grow carbon nanotubes, there is a certain probability PM that a carbon nanotube is a metallic carbon nanotube. People would typically tell you that PM is 1/3 or 33%. There have been growths that people demonstrated where the PM is 10%. That's great, but still there is a non-negligible fraction of these carbon nanotubes that will be metallic, and the remaining carbon nanotubes will be semiconducting, which is 1 minus PM. Now you can have a finer granularity of these things. You could say, well, instead of saying having this PS and PM, you will have something like you could grade them by their leakage and all that. That's all doable. Now let's say that you are building a carbon nanotube transistor now, and you decided to have 3 nanotubes under the gate. So what could be the situations happening? Well, I could have a situation where all my carbon nanotubes are semiconducting, and that probability will be roughly around 30%, assuming that PM is 33%. I could have 1 or 2 of my carbon nanotubes to be semiconducting and the remaining are metallic. And I could have a situation where all my carbon nanotubes under the gate are metallic carbon nanotubes, right? And now, even if I had a perfect metallic carbon nanotube removal process, right? I said 99.99% of the metallic carbon nanotubes removed. Let's take an ideal situation where 100% of the metallic carbon nanotubes were removed and 0% of the semiconducting carbon nanotubes are removed. That's kind of a great situation to be. I end up with a situation where this particular transistor does not have any carbon nanotube left. So essentially, I got an yield problem, right? So this is to show that this essentially becomes a probabilistic system, basically. And what's the probability of this happening? Well, 4%. 4% of a billion is a very large number, right? So what we have to do is we have to make sure that this particular probability is highly unlikely, right? It's a very small probability. Now, I could have 2 ways to do that. One way to do that is to say, well, I will have really wide gates so that I will have a lot of carbon nanotubes under the gate, so that it's almost impossible that I would have a situation that all my carbon nanotubes would be metallic or a certain fraction of my carbon nanotubes would be metallic. Now, that's a bad idea. The reason that's a bad idea is because now I'm wasting. I just told you that all this energy promise with these carbon nanotubes, and now I'm over designing my carbon nanotube circuits and I'm paying all this price. So that's why, number 1, I told you that it's very important to have advances in processing. So it's very important that the chemists keep working on getting their carbon nanotube fraction to be maybe 1%, maybe 0.1%. Even 0.1% or 1% of having metallic carbon nanotubes is not good enough. So you have to still use removal of this, using a technique such as VMR. But still, it would be highly useful because the additional costs that you have to spend for these kinds of things will go down very drastically. But we can play more tricks than that. And I will show you a trick in 2 slides. So the big picture, before I show you that trick, is that probabilistic modeling and probabilistic design will be a key component of these kinds of technologies. So essentially what we have done in our lab, in addition to doing all those technology work, all those design work, we have created this probabilistic framework where this person in the lab, what he can do is that he has all these equipments to control maybe the percentage of grown metallic carbon nanotubes, right? Maybe how to control the variations in the density of the carbon nanotubes, and I could list 20 other parameters that would not fit on a PowerPoint slide and satisfy my PowerPoint slide guidelines, so I do not have those. Similarly, on the design side, she can play a lot of tricks. She can come up with very special layouts. An example I will show you on the next slide. She can have very funny ways of doing carbon nanotube sizing using fancy algorithms and so on. I could come up with a long list over here too. But what matters is that this guy over here works very closely with her so that the overall system is co-optimized. That means you need an optimization of processing and design together so that the overall technology is something that I want, and I continue to keep the benefits of that I claimed right in the beginning of my talk. So I have to make sure that I satisfy the right kind of noise margins. I have to make sure I satisfy leakage. I have to make sure I satisfy my delay variations so that I can actually create an actual product. So let me show you this trick as an example, and this trick came up as a byproduct of going through this probabilistic design technique. So as I was talking about, we had this situation where you had these metallic carbon nanotubes, and when you removed, you had no carbon nanotubes left under a gate. So one thing that I could do is not to do anything, right? Which means, and by the way, this axis is 1 over cost. I couldn't find a better name for it. So of course, your yield will be very low. There is another thing to do, which is, as I was talking about before, which is that you upsize your transistors too much, that means 1 over cost goes down, that means cost goes up, but at the same time the yield goes up. And we have been able to verify all these things in actual fab. But there is a third technique that you can use, which is a new layout technique. Now typically when we talk about variations, so for example in CMOS circuits, everybody goes around and says, oh my gosh, I have variations and how do I deal with variations? Now in carbon nanotubes, it turns out that you can engineer correlations among various carbon nanotube transistors. Why? Because if you have a carbon nanotube that fairly runs let's say horizontally straight, which means that if you have 2 transistors that are placed on the same set of carbon nanotubes, those 2 transistors are going to have almost the same electrical properties, like that's governed by the carbon nanotubes. Versus if you have 2 transistors that are on 2 different sets of carbon nanotubes, those 2 transistors will be highly uncorrelated because the growth of the carbon nanotubes are highly uncorrelated. Now what it means is that so for example, when you are creating your carbon nanotube circuits, what you want to do is you want to do what we call an aligned active layout. That means the active regions of the carbon nanotube transistor should be aligned as much as possible. And if you can do that, then what would happen is that instead of having a chance of this carbon nanotube transistor not having any carbon nanotube left, or that carbon nanotube transistor not having any carbon nanotube left, you will either have a situation where all carbon nanotube transistors on a row have no carbon nanotubes left, or all carbon nanotube transistors on a row have carbon nanotubes in there, which is essentially what the yield people would call as clustering, right? So typically there used to be this what Murphy's yield model, which is essentially an exponential distribution, and then people figured out that the defects actually cluster, and that's why yields are higher than what would be predicted by that Murphy's model. The exact same thing is going over here. If I can have an aligned active layout, what I'm doing is that I'm clustering the failures of my carbon nanotube cells, which would mean that I would very significantly improve the yield of my carbon nanotube circuits. And it does not stop over there. Actually, you can even play layout design tricks where you would like to reduce the variations in the speeds of your carbon nanotube circuits by clever layout design, and those are possible. So I'm almost done. I would like to conclude my talk. First of all, I would like to thank the sponsors, without whose help, this work, wouldn't have happened. And I wanted to remind you about the carbon nanotube FET technology outlook. The key take-home message: mispositioned carbon nanotubes with this mispositioned immune design and the growth of the carbon nanotubes that I showed you, it is essentially a green signal right now. I think everybody agrees. Metallic carbon nanotubes, it's somewhere between yellow and green. We would still like the chemists to reduce the percentage of metallic carbon nanotubes so that all that variation stuff gets under control. We have high hopes for the carbon nanotube density. I didn't have time to talk about that today, but we'll be happy to chat with you about it. We are very excited about it. And of course, doping and contacts are something that our colleagues and collaborators are working on. So to conclude this talk, I hope that I could get across the point that it is extremely important to create imperfection-immune design for these, nanotechnologies, and that means that does not simply mean that you just slap a lot of redundancy and somehow hope that everything will work out, because then there would not be any hope, because whatever gains you would get out of the technology will be compensated for by the additional redundancy. That's why we have to have practical solutions, and I hope that I could get the point across that these new solutions that I showed you are practical and they're elegantly simple. Of course, the next challenge that we have to really nail down is the challenge of carbon nanotube variations, and we think that by using this idea of carbon nanotube correlation engineering through spatial layouts, we may be able to do that. So thank you very much for your attention, and I'll be happy to take questions.
Outstanding.
Thank you.
Really great stuff. The transfer process, pull off the carbon nanotubes from the quartz. Isn't that a place that you could do the metallic separation as well by using a thermal sensitive adhesion?
So that was our original idea. So our original idea was the following, that what we would do is, because then, I said, like, we would name this whole thing as pristine nanotubes or something like that, right? That's where you are going, right? So essentially, maybe, like before transfer or after transfer, I would just, like break down this metallic carbon nanotubes using my structure, and then I would do a clean deep processing, and then I will tell you, Dennis, here is my wafer, right? And that's the wafer supply basically, and everybody builds on these things. Two things that you have to worry about. One thing is that you have to kind of worry about the geometries a little bit, because it's not exactly clear that where the metallic carbon nanotubes will break, right? They could break very close to the contact, which would be great, but if they break in the middle, kind of you have to, make sure that you do not have any sort of a transistor that's sitting only on the fragment. But, we could get around that actually. But the bigger issue was that, so there is a funny story about this, that I would like to share. So, that was kind of our original thinking process. And, and when, I was talking to my student and I said, well, this deep processing is something that worries me. My student said, oh, don't worry about it. Deep processing is going to be very simple. Like let's focus on some other stuff. And I told him, well, he just jinxed it. What would happen is that this deep processing is the one that would just kill us at the end. Guess what? So, come January, the fab opens, right? SNF opens, and we keep working on these things, and we kept finding that after the deep processing, the contacts of the contact regions were the ones that were creating a lot of trouble, and we were not getting any contacts. So then what did we have to do? We said, well, like we have to come up with a technique where we do not mess with the contacts, and that's where this VMR came from, and that's why I keep making this point about that the contacts were not affected. Now, if somebody could come up, maybe there is a better process to do this thing that would get around some of those things, that would be terrific.
Anybody else?
Of devices that people actually make, what's a typical number of carbon nanotubes?
Right. So, I would give you the number in terms of density. How about that? So, typically when we grow carbon nanotubes in our lab, if we are in a really good day, and if you are lucky, we would roughly see something around maybe 5 nanotubes per micron or something like that, right? Remember, we have to achieve 200 nanotubes per micron. Now, what other colleagues at other places, what they have been able to do using some variations of the growth process, they have been able to get on good days at a wafer scale, I think they claim something around 10 to 15 nanotubes per micron. But other people have shown that maybe you can do double growth or something like that and could get up to 70 nanotubes per micron. And I think but those are at a smaller fragment level. So these are like kind of a single growth, double growth, or smaller fragments kind of thing. Now with this this multiple transfer technique that this undergraduate student has developed over here at Stanford, what he has been able to do is that he has been able to show that up to like maybe 5 transfers or more, he can keep increasing the density of the nanotubes. Now remember, increasing density is not good enough, because oftentimes people have shown stuff to us where their density is increasing but the on currents do not increase because of all these weird interactions between the carbon nanotubes. So it's very important that when you increase density, the on currents actually increase, right? So with the undergraduate work that I was just talking about got published in Nanoletters, he could show that the on currents would increase linearly, and so that was something really great. So we think that probably having a high density growth of nanotubes, maybe like if somebody could grow like let's say 20 nanotubes per micron at a full wafer scale, and now you could do 5 transfers, right? You got 100 nanotubes right there basically, or even more. So that could be possibly a scalable path toward getting this density up moving forward. Does that answer your question?
What holds the nanotube onto the silicon?
Van der Waals forces.
Sticky.
Well, I mean, the Scotch tape pulled it off the quartz,
Yes.
and then you put it over here.
No, the way this thing works is that we first put in gold, and then we put the Scotch tape, and then we peel off the whole thing, and then we transfer the whole thing back onto the silicon wafer, and then we put it in a thermo hot plate basically to peel off the Scotch, the thermal release tape, and then we etch out the gold. So that's why it's not just simply that you put in a Scotch tape and peel it off. It's not that simple.
So how does, I missed the step in there, how does the gold stick to the silicon?
So what you do is that you go and you glue these carbon nanotubes basically, and then you put a layer of gold, right? Like you deposit a layer of gold, and then you put the Scotch tape, and then you peel the whole thing off, and then on the
That's
silicon.
because the gold wasn't stuck to the quartz.
Right, exactly. And then you go and put the whole thing over there, and then you're not peeling off the Scotch tape. You're putting it on a hot plate. That's when the thermal release tape releases itself out of the gold. You're not peeling off
The gold isn't really stuck to the silicon.
Yeah, the gold is sitting on the silicon. You can think of almost you have the carbon nanotubes underneath, and then you have gold on top of it, and these carbon nanotubes are covered with gold, and that whole structure stays and when you put a hot plate, the in a heated chamber, basically the thermal release tape gets itself off.
Yeah, but after I've taken the tape off, is there anything really holding the gold in the right place?
Yeah, you're just sitting on your wafer, right, with a layer of gold.
Yeah, if I turn the wafer upside down, can I shake it off?
I do not know the answer. I have not tried that.
So, can you describe, is it 10x better because the current density is higher, or because the parasitics are lower?
So there are 3 points actually. So first of all, like very good mobility, and better parasitics and better electrostatics. These are the 3 reasons why like you could get that. That's the Professor Philip Wong actually has a good model that you can even download and simulate some of these things.
Thank you very much.
Thank you.
For more, please visit us at stanford.edu.